aspirant, welcome to the capsule number 3 of electromagnetic waves. So far you have seen the two capsules and this is the capsule number 3 on EM waves. Now in the last class, we emphasizes on the four Maxwell equations, that how the four Maxwell equations are formulated, what are the problems involved in that. And in this class, what we are going to do, we are going to focus on the some of the theoretical aspects which are connecting us to the next topic. So let me give you an idea. So number one topic is very important from the interview point of view. So the first topic is not very important from the exam point of view, but it is an extremely important topic from interview point of view. So this topic is magnetic charge. What is magnetic charge? Magnetic monopole also you can think. Let's say we live in a world where magnetic monopole can exist. Means we have the magnetic monopole. Let's say we can have a North Pole individually, or we can have the South Pole individually. Let's say we are in this world. Although in our world, North and South cannot exist individually, but let's say we are in some sort of world in which North and South Pole can exist individually. In that situation, how your Maxwell equations will change? Will those days remain same or something will change as such? So the answer is definitely yes, something will change and we want to see that change. Okay. So first of all, let's see that are the Maxwell equations symmetric? Means whatever electric field is doing, does the same thing magnetic field is also doing? Are they symmetric or not? So let's consider the first case in which we are in a free space. So we are in a completely free space. Our rho is 0, means no charge exists and no current exists. So there is no free current, no charges are there which are sitting, and no currents are there. So we have rho 0 and also we have J 0. In that situation, our four Maxwell equations will become del dot E is 0, because del dot E is nothing but, let me change the pen. So del dot E is nothing but rho by epsilon naught. So if rho is 0, then del dot E is 0. Del dot B is anyway always 0. Del cross E is minus curly B by curly T, and del cross B is nu naught J plus nu naught epsilon naught curly E by curly T. This thing becomes 0. How symmetric is this equation? Very symmetric. The divergence of electric field is 0. Yes. The divergence of magnetic field is 0. Yes. The curl of electric field is changed in magnetic field time, curly B by curly T, and del cross B is curly E by curly T. You can ignore the constants, right? Constants are just representing the how much the magnitude is, but the dependence is same. So if you change magnetic field with time, you get electric field. If you change electric field with time, you get magnetic field, and divergence for both of these is 0. So very, very good symmetric equations are there. So these are, in this situation, Maxwell equations are completely symmetric. So if you are in a free space, electric field and magnetic field both are behaving in the same way. So you should remember this situation. If you are in a free space, so focus on the statement I am referring here. If you are in a free space, electric field and magnetic field are behaving in the same way. They are symmetric. So if you are replace electric field by magnetic field, so let's say wherever your E is there, you put B, and wherever you have B, you put minus nu naught epsilon naught E, then you will get the same equations back. So if you just replace E by B and B by minus of nu naught epsilon naught E, you will again get the same equations back. So it's a very completely symmetric situation. However, if you are in a medium where actually the charge is there, where actually the free currents are there, then the symmetry is broken. And how that symmetry is broken? Then you have these four equations. So del dot E is rho by epsilon naught, but del dot B has nothing here. So it is 0. So some term is missing here. Right? You can imagine that. And this is missing because there is no monopoles. No monopole is there. So del dot E is equals to charge by epsilon naught. So individual charges can exist. Individual positive charge can be there. Individual negative charge can be there. That is why we have the rho here. So electric rho can be there. You can have the electric charge, but you do not have the magnetic charge. So rho m by epsilon naught. Although here we should have rho m, but rho m does not exist. That is why we are getting 0 here. That is why we are getting 0. And if you see del cross B, you get nu naught J plus nu naught epsilon naught curly E by curly T. So this term is here and this term is there. That is symmetric. But what about this term? There is nothing similar to this term here. We should have something similar to here, but we don't. Why we don't have anything similar here? Because why is this term coming? Because the charges are moving. Which charges? Electric charges are moving. That is why we are getting this J, current per unit area. But we do not have any magnetic charges. So if the magnetic charges also move, we will have electric field. We will have Jm. But Jm is missing. Why Jm is missing? Because there is no free magnets, free monopoles. There are no free magnetic charges, and those magnetic charges cannot move as such. If magnetic charges are not there, what is moving? Nothing is moving. So two things are missing. One is magnetic charge as such. That is why in this term, something is missing. In this also one thing is missing, that magnetic charges, if not exist, then how will they move? So the magnetic charges is missing and the current due to magnetic charges is also missing. That is why our equations are not symmetric anymore. You can see one thing is missing here and one thing is missing. So if we consider that, yes, let's say we have some world in which actually there is some magnetic charge exist. So we will have magnetic charge density, which is rho m. Let's say you have this much north pole in this volume. So south pole is not there, only north pole is there. So north pole per unit volume will be defined as rho m. And if that north pole starts moving, then you will have the current density as well, which is Jm. So if you have rho m, you have Jm, then your four Maxwell equations will become this. Del dot E will be rho E by epsilon naught. What is rho E? Electric charge. However, del dot B is nu naught into rho m. What is rho m? Rho m is the magnetic charge. Now, if the charges are there, then they will also move and they will also have the current. So here we had nu naught Je, here we have nu naught Jm. So the sign between this and this is same. So if this is positive, this is also positive. But in this case, minus curly B by curly T. So here also I will get minus of nu naught Jm. Epsilon naught is replaced by nu naught. That's it. That's it. So one term will come here and one term will come here. Here the term is coming in this equation because the magnetic charges are existing. And here the term is coming because those magnetic charges are moving and giving the current. Okay. So that is how your magnetic field, your Maxwell equations will change in the situation if you actually have magnetic charges. Let's say you can have individual North Pole and South. The above topic is very important for interviews. Why I am saying that? Because in one of the interviews, I have also taken, this question was asked to me. I have personally given 30 interviews. I can count on my fingers 30 interviews of physics, and I am not including the interviews which I gave for job. For teaching job, but the interviews I gave, I am not including that. I'm only telling you the interview experiences of integrated PhD and PhD. So 30 interviews at many different places, ISERs, IISc, IITs, HRI, Saha Institute, Tata Institute, TIFR, selected twice in TIFR, ICTS, IMSC, right? But RRI, all the institutes have given interviewing. And that is one of the most important thing that my students benefit from. Once they qualify the exam, and if they have any interview call, I take their free mock interview. If they are my student of my course, I take their free interview. So if you are already in the course, always remember, if you qualify the exam, any exam, and if you have any interview coming up, I will take your free mock interview. Okay. I have done it in the previous years also. This year also it will continue. Okay. Because I know many questions which can be asked in the actual interviews. Okay. So this is an important topic from interview point. Now I want to shift to the something which is actually not an extremely important topic, but the questions have actually came in exam. You can actually see the questions in exam and we cannot leave this topic. And that topic is electromagnetic waves in matter. So now you are not moving in a free space. Now your waves are inside a matter. So whenever you are in a matter, some material, materials can be of two types. One is magnetic material, one is insulating material. Materials can be of many types, but here I want to refer to the two types of material. I want to divide my material into two properties: magnetic properties, electrical properties. If I divide my material into magnetic properties, then I call them magnetic materials. And if I divide them into the terms of electrical properties, I say they are dielectric or something. Dielectrics. Let's say insulators. So whenever I am in a magnetic material, the term that I use is the new term I define, and that term is known as capital H. This capital H is known as magnetic field intensity. Okay, so let that thought sink in you. Learn from the curiosity. Don't just learn because I am teaching you something. Now you are inside a material. Your waves enters the material. The more relevant thing is you define H. H is very useful to define. And what is this H? That is what I'm going to teach you. So many questions might have came to your mind. Why H? Why H is more relevant? Why it is H? What are we going to do with this? Why not we just use B, which is magnetic field? So let's try to answer all these questions. So first of all, H is known as magnetic field intensity. Second, it is defined as, capital H is defined as B divided by nu naught minus M. Okay. Now the more questions arose. What is B? B is known as magnetic flux density. I will come to the point that what is the difference between H and B. Understanding this difference is very important. Minus M. What is M? M is known as magnetization. And this magnetization is equals to chi into H. Okay. The relation or formula for magnetization is chi into H, and this chi is known as susceptibility. So this is the facts. I'm not giving you any reasoning, logics, anything. I am telling that these facts are important. I'm just changing the sequence of learning. I'm first giving you the facts so that when you go to the exams, you know that what facts I need to know before going to the exam. And then I'm going to tell you that what is the background of this facts. So now let's enter into the background part. So you have some magnetic material, beautiful, and you place it in a magnetic field intensity. Whenever you turn on any instrument, any electromagnet, it does not produce B, it produces H. Always remember this. So let's say I turned on my electromagnet. Now electromagnet is producing something. It is not producing B, it is producing H. So what your instrument is producing is magnetic field strength or magnetic field intensity, which is H. So you put your magnetic material, any magnetic material, let's say iron. Iron is the best magnetic material. Or you can say any diamagnetic material. For example, cuprous sulfate solution. Blue solution, you remember in the chemistry labs, you have blue kind of solution. Or oxygen. Oxygen can also be considered as a magnetic material. Oxygen gas you have. This oxygen gas you put up in the H, magnetic field intensity, which is coming from your magnetic instrument, which is producing that. Once you do that, your material will get magnetized. What do I mean by magnetized? Means this material had some north pole, it had some south pole, both of them were existing here. Now the material gets separated. The molecules started getting separated. South pole gets separated, north pole gets separated. So now the molecule was like this. It was like a sphere. Both north and south were sitting in the center. Now once you do it, your north and south get separated and you get magnetic dipoles. Magnetic dipoles. So whenever you have south on one side and north on one side, this is known as magnetic dipole. Just like an electric dipole, you have magnetic dipole. So your south and north get separated, and inside that you are produced, you have generated what you have generated. What you have generated? You have generated magnetization. You have magnetized your material. Your material has now become magnet. For example, if you place iron, you take an iron block, and you place it in a magnetic field intensity. That iron will also become magnet. Why that magnet? Why that iron is also magnet? Have you ever thought that if you have iron and if you have another iron, if you touch both, they will not attract each other. There is no force of attraction between them. They both are not magnetic. But if you place this iron in front of magnet, they both attract each other. It means this iron also become magnet. Only two magnets can attract. Only two magnets can attract. So when I place this iron in front of magnet, this magnet attracts the iron. It means iron is also now magnet. So whenever you place a magnetic material in front of magnetic field intensity, it gets magnetized. What is the meaning of this magnetized? So magnetization, how much it is magnetized is defined by magnetization, M. How much is your material magnetized? That is defined by capital M, and it is known as magnetic movement per unit volume. How much is a magnetic movement divided by how much is the volume of your sample? That is known as magnetization. I have taken an entire lecture on magnetic movement in my course. I am again and again saying, if you are preparing for CSIR NET, GATE, JAM exam, and exam is coming up, if you want to cover the syllabus fast, you can join the course, and all the lectures you will get are the short lectures which will cover all the topics. So you can consider joining that course. I have also reduced the fee of the courses. Okay, because only few months are left. So my courses are best quality, and also they are minimum in price. No one is offering the courses at that price. That is my guarantee to you. And the quality is not reduced even a little bit. Okay, nice. So magnetization is how much is magnetic movement divided by volume. So you can clearly see I had that magnetic sample in front of me, and in the magnetic sample I put it in the H. When I put it in the H, what happened? South and north get separated. As a result, I produced M. Magnetic movement has been produced, or magnetization has been produced. So this is my M. Magnetization is always from south to north. Always remember, it is also always from south to north, because dipole movement is from south to north. So this is my situation. So now H is what I applied, but that is not important. The net field inside the material is B. You applied H, that is fine. But how much of those lines are entering the material? That is B. Let's say you have a ferromagnetic material. Then the field lines try to go through this. Means you applied H, but the field lines entering are B. Field lines per unit area is B. Field lines, how many field lines entering per unit area is defined as B. How many field lines are entering per unit area is defined as B. H is something that you applied. B is something how many lines per unit area are entering. So both of them are different. One is what you are applying, and another is what is the behavior of H inside the magnet. So the behavior of a magnetic field inside the material is defined by two things. Number one, what you applied H, plus what is your magnetization inside. Because magnetization inside will also produce some magnetic field. So you also produce, because you are magnetized. So now that magnetization will also produce some magnetic field inside the material. So inside the material, magnetic field is because of the two parameters. One is what you applied H, plus one is your magnetization. So both these effects combined give you B. So B is the effect of H plus effect of M, or you can say the effect of H is equals to effect of B minus effect of M. So this is an equation that you can clearly see. The H is equals to effect of B minus effect of M. Okay, so in order to keep the unit same, you have to divide B by nu naught. That is very important, because in this entire theory, what includes actually is nu naught is the only thing that includes the features of the material. If it is an iron, if it is a aluminium, gold, what is it? So that is defined by term nu naught. So H is equals to B by nu naught minus M. Now you understand from where this formula came, because B is something which is inside, and that is made up of two things, H plus M. What I applied plus what is magnetized inside. So if I take M on other side, then H will become B effect minus M effect. That is how your formula came. Now M, I already told you, is chi into H. So what you can do, you can bring this chi on other side. So you will get 1 plus chi H equals to B by nu naught. What you can do is you can take B here and nu naught you can take on other side. This entire thing is known as nu. 1 plus chi nu naught is known as nu. So B is equals to nu H. And what is nu? Nu is the permeability in the medium. Nu is the permeability inside the medium. So always remember B is always equals to nu times H. Always. B is equals to nu times H. And nu is the permeability inside the material. And it is equals to nu R into nu naught. I already told you nu is equals to nu R into nu naught. And nu R is given by 1 plus chi. These all the formulas are important. I'm telling you beforehand that question have actually came from this formula as well. That nu R is equals to 1 plus chi, where chi is the susceptibility. So the only thing that is left to discuss is what is this term susceptibility and what is this term telling us. So this term is telling us, so I already told you, right? M is equals to chi H. It means chi is equals to M by H. Means how much magnetization you produced and how much was the field you applied. So how much your material got magnetized on applying how much field. So this tells you that how easily your material can be magnetized. So in order to magnetize this material, you are applying H. So how easily your material can magnetize, that is what your susceptibility tells you. Okay. So these are all the formula that you might require in magnetism in materials. Now let's come electric field in materials. What about if we are now think about electric field? When we are thinking about electric field in matter, we have to go to the electrical properties. So now let's say you have some dielectric material. In dielectric material, you define the term known as displacement vector, which is known as D vector. And D vector is written as epsilon naught E plus P, where P is the polarization of the material. So let's say you have some dielectric, you know that this is dielectric, and you apply electric field. What you are applying now? Electric field. In the previous case, what you were applying? H. In this case, what you are applying? You are applying E. As a result, negative charges will come on this side, positive will come on this side, and inside you will have the dipole moment. You will generate some dipoles, means negative and positive charge will get separated and you will generate some dipoles. Again, I'm telling, if you want to know what is dipoles, lectures are covered in detail in course. So what is dipoles? So dipoles are produced in the material. As a result, polarization. What is polarization? Dipole moment per unit volume. In the previous case, what was magnetic dipole moment per unit volume is capital M. Electrical dipole moment divided by volume is capital P. Both of that was magnetization. This is polarization. P was chi into B. P is chi into H, sorry. P is alpha into E. Alpha is polarizability. Polarizability tells you how easily material can be polarized. Chi was telling you how easily your material can be magnetized. So same thing. Everything is going out to be same. In this case, you applied electric field. As a result, negative and positive charges get separated. Why they will get separated? Because you know negative charges will experience the force on this side and positive charges will experience the force on this side. Positive charge experience force in the direction of electric field. Negative charge experience the force opposite to the electric field. So negative charge comes on this side, positive charge on this side. You generate a dipole moment, or you can say you generate the polarization. Now, electric field inside will be because of the two terms. Because of the two terms. One is because of the electric field and one is because of the dipole moment. That is why you can clearly see the electric field inside. How many lines are passing per unit area? That is known as D. How many electric field lines are passing per unit area through the material is known as D. And it is made up of two things. One is what you applied. You applied electric field. And what is the polarization inside? Same thing like before. So your B was made up of two things, H and M. Now your D is made up of two things, E and P. In order to conserve the units, you have to multiply with epsilon. And P is what? P is alpha into E. So let's put this value. D is epsilon naught E and P is alpha E. So you will get new epsilon naught plus alpha E, and epsilon naught plus alpha can be written as epsilon. What is epsilon? Epsilon is the permittivity in the medium. So you have to remember this formula that D is always equals to epsilon E. That is the situation we get. So now we will modify our Maxwell equations. So del dot E equals to rho F by epsilon. So always remember, whenever you have to modify your Maxwell equations, you always modify those equations which contains the free charge or free current. Which does not contain free charge or free current, you don't have to change those equations. If you want, you can, but that is not required or that is not necessary. Only necessary requirement is you change the equations which includes the free charge density. Perfect. Let's see. The situation in hand now is that you have the equation del dot E equals to rho F by epsilon. You don't have epsilon naught, you have epsilon. Why? Because now you are in a medium. In a medium, you cannot define epsilon naught, you can define epsilon. Because permittivity in the medium is epsilon. You take this epsilon on the other side, you will get del dot epsilon E equals to rho F, and epsilon E we just study is B. So your equation becomes del dot E equals to rho F. You are comfortable with that? Equation is satisfied. Then del dot B equals to 0. You don't have to change this equation. Why? Because it does not include any free charge. Del cross E equals to minus curly B by curly T. You don't have to change this equation because it does not contain any free charge or any free current. You can change. I'm again and again telling, if you want to change, you can change. You can put E in terms of D and you can put B in terms of H. But that is not required. If in the question it is demanded, you can do it. You know the formula of D and B in terms of E and H. If it is required, you can do it. So all the formula that you need to remember is D equals to epsilon E and your B is equals to H by nu. Sorry, nu H. That's all. That's you need to remember. Right. So I hope you understand. So now let's consider, let's change the fourth equation. Fourth equation is del cross H. So I did something wrong. Yeah. Here it is del cross B. Del cross B equals to nu into JF plus nu epsilon curly E by curly T. Now if I take this nu on this side, I will get B by nu, and B by nu is nothing but H. So this B by nu will become H. So I will get del cross H, and this JF will remain as such, and this nu comes here. Epsilon into E can be written as D. So curly D by curly T. So del cross H can be written as JF plus curly D by curly T. So this is your fourth Maxwell equation. So this is how you write your Maxwell equations in terms of H and D. Okay. So that was the thing. So I told you what will happen if magnetic monopoles exist. Then we saw that how your magnetic field changes if you are in a magnet or magnetic material, and how your electric field changes if you are in a dielectric medium. And then we saw how your Maxwell equations will change. Now what I'm going to give you is boundary conditions. Summary of the boundary conditions. What is the summary of all the boundary conditions that you need in the electromagnetism? Many questions, many questions you can see which have been asked in the previous year questions. Any exam, JAM, question have came. Just question came. TIFR question came. GATE question came. NET question came. BARC question came. There is not even a single exam in which boundary conditions question does not came. So it's an important topic. So let's see the summary of all the boundary conditions. So first of all, let's try to understand what is parallel and what is perpendicular direction. Let's say you have any plane, any surface. So one of the surface I'm showing you, the surface is in the XZ plane. So this is your x-axis, this is your y-axis, and this is your z-axis. and this surface is in the XZ plane. What are the parallel directions? The parallel to the plane, x-axis is parallel to the plane, z-axis is parallel to the plane. So x and z are the parallel directions. However, y is the perpendicular direction. In this case, this is in xy plane and z is passing perpendicularly. So x and y are the parallel lines and z is the perpendicular to the plane. Okay, this is simple idea. So usually what happens is you have one medium, you have another medium. Let's say this air water situation. You have air, which is one medium, you have water, which is another medium, and this is the plane which is dividing both the mediums. So this is a boundary between the two mediums. Now, sometimes this boundary also have some charge, or sometimes this boundary also have some current, K. So sigma is charge per unit area and K is current per unit length. Okay. Sometimes the boundary which is dividing both the mediums, medium 1 and medium 2, has sometimes have some charge. So we define charge per unit area, or sometimes it has current and we define current per unit length. Why we are defining current per unit length and not current per unit area? The question might have came to you. Let's say this is your surface and current is flowing like this. What I do is I take the strip. We have the restriction. What is that restriction? Why we have to define current per unit length? Why not area? So let's say you have wire and in the wire you have charge Q. So you say lambda per unit length. If you have surface, you have charge Q, you say charge per unit area. And if you have volume, you say charge per unit volume. For charge, it is okay. But what about current? If you have wire and if you have current, you do not say that you contain current per unit length. If you have wire and you have current, you say you have current. You don't say you have current per unit length. Why? Because in order for current to flow, you at least need a wire. Na? You cannot have current at a point. You have to have current in a wire. So if you have a wire and if you have current, you say, oh, you have current. If you have surface, then what do you say? The current divided by perpendicular length, L. So current is flowing in this direction and length is cross-sectional length. Then you say I by L. And if you have volume, let's say this, then your current is coming and then you have area. So then you say current per unit area, which is J. So you say current per unit length, current per unit area. So whenever you have two-dimensional body and the current is two-dimensional, you don't say current per unit area, you say current per unit length. And that is defined as capital K. So sometimes I am saying that boundary also have sigma, charge per unit area, or current per unit length, sigma or K. The number one boundary condition is that D1 perpendicular means, let's say you have this surface and Z is a perpendicular axis. So D1 in Z direction minus D2 in Z direction. So Z component of displacement vector on this side is D1. Z component of displacement vector on this side is G2. So D1Z minus D2Z is not continuous. So they both are not equal. They are not continuous. They are discontinuous. How much they are discontinuous? Sigma F. Whatever is the charge on this plate. So D1 perpendicular minus D2 perpendicular is sigma F. If there is no charge on this boundary, then it is continuous. And if there is a charge on this boundary, then it is not continuous. Which makes sense. Perfect. Second, epsilon. So D can be written as epsilon into E. So epsilon 1 into E1 perpendicular minus epsilon 2 into E2 perpendicular equals to sigma F. So perpendicular component of electric field and displacement vector are not continuous. Can I give you the feeling of this? I should try it. I should try it at least. I do not know how your basics how good your basics are, but let's say I'm assuming that you have good basics. So let's say you have electric field coming up. Some external electric field is coming up. And in the first case, let's assume there is no charge on this boundary. So this electric field will come and pass through it. So electric field on this side and electric field on this side is same. But now let's say I have this charge sigma. So this sigma will produce sigma by 2 epsilon naught on this side and sigma by 2 epsilon naught on this side. And electric field was coming throughout. So on the left hand side, your electric field is E minus sigma by 2 epsilon naught. And on the right hand side, your electric field is E plus sigma by 2 epsilon. So what is the change in electric field? So E plus sigma by 2 epsilon naught. Okay, I should say 2 epsilon 1 and 2 epsilon 2. Or let's assume that both sides are equal, epsilon naught, epsilon. This medium also have a air, this medium also have air. So electric field on this side minus electric field on this side. E will cancel and basically you will get sigma by epsilon, which is exactly what you want. If you have epsilon 1 and epsilon 2 both epsilon naught, so if your epsilon 1 and epsilon 2 are epsilon naught, this epsilon naught will go on this side, then your E1 perpendicular minus E2 perpendicular will be sigma by epsilon. So you can clearly see the same thing we are getting. So the change in electric field is not there if this boundary has no charge. But if this boundary has some charge, then the perpendicular component will become discontinuous. That is the situation that you need to remember. Okay. So this is a situation if your charge density is 0. However, the magnetic field perpendicular component is always continuous. Does not matter if you have charge, if you have current, whatever you have. If your boundary have charge or current, your perpendicular component of magnetic field will always remain same. Similarly, your parallel component of electric field will always remain same. Does not matter if you have charge or current. The parallel components of electric field. What parallel components? Parallel to the plane. So if plane is in xy, then the electric field along x and electric field along y will remain continuous. What is the electric field along x on this side? The same electric field along x-axis will be on the other side. In both the mediums, electric field along the x-axis will be same if your boundary is in xy plane. And then in the last, but you can say that your parallel component of magnetic field or H vector is not constant. If you have current in the boundary, then your parallel component will not be same and your condition will be H1 parallel minus H2 parallel KF. K is the current per unit volume. Oh, sorry, current per unit length cross N cap. N cap is the perpendicular direction to the surface. So if your surface is along XY, then N cap will be Z axis. So the most used ones are these ones. So I have summarized all the relations that you might be requiring. And I have summarized this. So you can look at this and you can make your own notes. You can look at all this. You don't need the derivation of any of these. And this is most important boundary conditions and no question will come outside this. All the boundary conditions, the formulas that you require is coming from this. Okay. So I want to discuss one question before I end this lecture. And that question is that you have an electromagnetic wave and it is propagating in a non-magnetic material. Okay, I agree that. Non-magnetic material means that nu is equals to nu naught. However, it has a relative permittivity, means it is in a dielectric material and epsilon is equals to epsilon r into epsilon naught and epsilon r is given to you as 4. So you know epsilon is 4 epsilon naught. So H vector is given to you and they are asking what is electric field. Okay, so this is your homework. In the first and second capsule, I taught you that how to go from B to E. And in this class, I taught you how to go from H to B. So first of all, go from H to B and then go from B to E and try to see what is your answer. Your answer number A should come out to be correct. So this is your homework. Try this question. This is from the previous year question of CSIR net exam. Okay, so that was about capsule number 3. Capsule number 4, 5, and 6 are extremely important. 4 capsule include pointing vector, intensity, pressure, all those formulas. Capsule 5 and 6 contains electric field in dielectric material and electric field in conducting material. So many questions we have seen coming from this topic. So stay tuned and I will request you, if you are not the part of the course or you are watching me first time, Also share these videos with your friends. Send these videos in your class groups so that more and more people can connect with us. Okay, so that's my request. If you find the lectures useful, you can do that. Okay, so that's all for today. I see you in the next class.